Good evening. This is Jay Yablon. Let's talk about physics. This is the second talk in a series of talks that I'll be putting together regarding those aspects of known physics which are likely to play a key role in the unification of general relativity with quantum mechanics. That unification being one of the most important outstanding problems unsolved in theoretical physics today. In the first talk about 10 days ago, we did a retrospective from the early 2020s of the work that Wheeler did in the 1950s regarding the geometrodynamic vacuum. Here we are 65 years later. That vacuum, as Wheeler talked about it, as we summarized in the original talk, has a series of Planck mass-sized fluctuations which are separated from one another by the Planck length, and they're so densely packed that they fit within their own Schwarzschild radii, and so they are individually black holes, and collectively they are densely packed black holes. Extremely high densities on the order of 10 to the 90th kilograms per cubic meter. That's extremely dense, obviously. Now we know, which we did not know back at the time of Wheeler, that black holes are not black in the sense that we thought of them then, because as discovered by Bekenstein and Hawking in the 1970s and into the early 1980s, black holes have a radiation spectrum. They emit black body radiation, and the black body radiation, of course, is given by the Planck curve, which is up here, and people should be familiar with that. By the way, in this talk, I've put the key equations that we're going to go through already on the board, so that should speed up the time for the lecture, and you don't have to sit here and watch me try to write these equations on the board. In any event, the most important thing that we now know is that that vacuum which Wheeler talked about is really a collection of black holes, indeed one omnipresent black hole, but because of what Hawking found, because he found that black holes emit this, that vacuum itself has a radiation spectrum, and that the temperature associated with that spectrum is very high, on the order of 10 to the 30th Kelvin. And obviously, when we left off last time, one of the questions was, well, if this vacuum, which permeates everything, is that hot, why aren't we burning ourselves? How do we exist? And I talked a little bit, preview, how one way to understand that may well be in terms of reciprocity relationships, reciprocity between energies and lengths, such as we see emerging from canonical quantum mechanics and the uncertainty principle. And in the case of radiation, reciprocity relations between temperature and length, and in particular temperature and wavelength. One of the most familiar of those relationships in the temperature domain, of course, is the Wien displacement law. And that law says that in the Planck spectrum, there is a peak wavelength, where the maximum is reached. You just take the derivative, set it to 0, the derivative of that with respect to that, set it to 0, and you get a peak. And that peak is always, no matter what the temperature, located in such a position that the temperature of the black body times the peak wavelength, which sits up here, is 2 pi hc over a constant A times the Boltzmann constant. And the constant A over here is equal to this, 4.965, and it is computed in the course of taking the derivative of this spectrum and finding its maximum by setting that to 0. So those are That's what we went through somewhat last time. Now we're going to talk more about black holes. And the title of tonight's talk is After Hawking, How Black is a Black Hole? And we're going to look at that particular question. Obviously, prior to understanding that black holes emitted a radiation spectrum, black holes, well, let's go back to the beginning. General relativity comes out. It's published, I believe, in the fall, early winter, November, December of 1915. And a month later, in January of 1916, Schwarzschild publishes the very first non-trivial exact solution of the Einstein equation for a non-rotating stationary mass. It's just a mass that's sitting there. And for the space-time in the vicinity of that mass, and the Einstein equation being nonlinear, of course, gives you allows you to discuss and understand and calculate for extremely strong gravitational fields and extremely dense masses, something that obviously Newton's theory doesn't do. It's simply a limit in a limiting case for relatively weak gravitational fields. And that was the first non-trivial solution. Of course, Minkowski, prior to 1910, found the first trivial solution, and that was flat space-time. But here in curved space-time, we have the first non-trivial solution, and that solution showed that any mass has that the space-time in the vicinity of a mass has a singularity at a radius r sub s, known as the Schwarzschild radius, which is equal to twice the gravitational constant times the mass over c squared. This radius is a very small radius, and by the way, we're going to use tonight the Schwarzschild diameter, which is simply twice the Schwarzschild radius. It will be simpler to talk about for reasons that will become apparent as we go on. But when we're talking about a Schwarzschild radius, excuse me, when we're talking about a Schwarzschild radius, every mass in the universe has a Schwarzschild radius. I have a Schwarzschild radius. This has a Schwarzschild radius. Everything has a Schwarzschild radius. But the Schwarzschild radius, when you calculate it out, g is a very small number. C squared is a very large number, but it's in the denominator. So the Schwarzschild radius is very tiny. For an object to become a black hole, to be a black hole, all of its mass has to be behind the Schwarzschild radius. So it has to be extremely densely packed within the radius, excuse me, which is given by this equation here. So once that happens, and again, let's go back pre-Hawking, pre-Bekenstein, when we didn't know about the radiation spectrum. What we knew is that if you had a mass that was compacted within its own Schwarzschild radius and therefore very dense, the space-time would be so curved that you wouldn't be able to obtain any information or anything whatsoever from behind that Schwarzschild radius. It was simply a great unknown with nothing coming out of it, with no information available, and hence it was referred to as a black hole. Of course, we now know that as a result of Hawking, that the black hole emits a black body spectrum of Planck, and that the characteristic temperature for that spectrum, Boltzmann's constant times the temperature, so that we were getting energy dimensions on the left side of this equation, is h, this should be h bar, excuse me, c cubed over 8 pi gravitational constant times the mass. That's the temperature of a black hole. And because the mass and temperature are inversely proportional, larger masses have lower temperatures. So cosmological black holes, the ones that we're trying to watch with our telescope from, billions of light years, or at least hundreds of millions of light years away, are going to have very large masses and very low temperatures. Now, intuitively, on first reaction, you may think, well, wait a second, don't large energies give you large energies, and generally you'd expect them to scale, but it's the opposite for black hole because of the fact that extremely massive, extremely dense objects are going to gravitate very strongly. They're going to pull everything back. They're going to withhold things. So the spectrum that you get and the wavelengths of the photons in that spectrum are going to be extremely long, and the photon energy is very small because of the withholding of that energy black hole by the black holes. On the other end of the spectrum, which I suggested that people who are thinking about cosmological black holes all the time give some thought to the ultra tiny black holes at the Planck scale, you have the reverse, because now the masses are very small. Planck mass is a very tiny mass, but that makes the temperature extremely large, and that's how you get to temperatures on the order of 10 to the 30th when you're talking about Planck masses that are compacted within their own Schwarzschild radii, which are on the order of the Planck length. So black holes are now not black, and especially the small black holes are not black in that usual sense because they emit a radiation spectrum which was not expected previously. If we take, now we're going to just do a calculation here. If we take the Wien displacement law over here, and we look at, let's just flip it around, 2 pi h bar c over alpha, we're going to put the k on this side now, is equal to the peak wavelength, which is up here, times Boltzmann's constant times the temperature. And now for a black hole, simply take the temperature of the black hole from here, substitute it into here, and what you get is this. You get that lambda peak wavelength up here, times h bar c over 2 pi times the Schwarzschild diameter. Again, we're going to use the diameter, not the radius, that these are all equal. Take this equation, restructure it, and what you find, given the value of A up here, and the trigger here looks a little lame, so let's get that fixed, okay. What you find is that the Schwarzschild diameter over the peak wavelength is equal to A over 4 pi squared, and that's 1 over 1.795 and a bunch of digits after this. And let's, for purposes of discussion from here, say that it's approximately at 1/8. So the Schwarzschild diameter of a black hole, of any black hole, is situated at about 1/8 of the place where you have the peak in that spectrum. So let's say here's half, here's a quarter. Let's go right here, and let's say if this is 1 over here, that this is 1/8 over here. So black hole, any black hole, that's its peak. Schwarzschild diameter is at 1/8 of the peak. Very straightforward calculation to do, and try it yourself using these things. And by the way, at the end of my talks, I photographed a blackboard and I post it on YouTube next to the video of these talks also. So, you know, you can look at these close up. A couple people asked me for a better view of the blackboard, and I think that's one way to do that. So, okay, this is where we are. And the other relationship, if you again do the calculations using the things we have here, you can also find out that the temperature of the black hole times its Schwarzschild diameter is equal to 1/2 h bar c over 2 pi times Boltzmann's constant. If you compare this here, you'll see that these are essentially the same equation, but now we're using the Schwarzschild diameter rather than the Wien peak wavelength because now we know that. One of the things that's important to note here is let's compare this relationship. And, you know, if you put the kappa in front here rather than over here in the denominator, then you have kT, which is energy dimensions, times a length dimension, and it's equal to 1/2 h bar c over 2 pi. And that has a very similar form, a very similar feel, and it's important that it does, to the uncertainty principle and to the measurement limitation that's derived from the uncertainty principle, which we talked about last time. Uncertainty principle, here you've got the standard deviation of momentum in a particular dimension. Here you've got the uncertainty in position, and this should be a J, not an I, is equal 1/2 Kronecker delta Ij, just in space, times h bar. And the measurement limitation, which it's well known how to derive out of the uncertainty principle using pair creation when you get two electrons, or when you get, an electron and a positron, twice the total energy. Basically, you use that in the derivation from the uncertainty principle. You find out that the energy in particle physics that you apply to any system times the spread in the radial resolution, Heisenberg's microscope, is greater than or equal to 1/2 h bar c. So this sort of relationship that we get for a black hole, which emerges from general relativity. Black holes come out of general relativity. They're not quantum objects. But then when you get to finding that these general relativistic objects have a black body spectrum governed by Planck's law, which came out in 1901 and kicked off the quantum revolution, all of a sudden you're seeing, well, wait a second, how is it that these black holes, which are a paradigm for general relativity, have something that is quintessential quantum mechanical? Well, as you start to look closer and you dig into that, you see that you get relationships where an energy dimension, and again, I'm going to move the K so we really have the dimensions very clear here, so we can match this up. We're going to put the K back over here. You have an energy dimension kT times a Schwarzschild diameter is equal to 1/2 h bar c. And this looks an awful lot like this. And in fact, the only difference here is a factor of 2 pi. And in quantum mechanics, 2 pi is used to develop reduced constants. So for example, we know that, let's find some space for this, h bar is equal to h over 2 pi. I mean, this is very well known. So in a very basic sense, what we find out here in the black hole when we look at the Schwarzschild diameter is a relationship with temperature that looks an awful lot like this. Coming out of black holes, but looking at something that's in the uncertainty principle. And the uncertainty principle, of course, derives from the canonical commutators of Heisenberg. When we talk about canonical quantum mechanics, we're talking about these Heisenberg matrix operators, which are non-commuting and which give you, which are equal to h. And from those, you derive the uncertainty principle. And you derive this measurement limitation, and it looks an awful lot like what we have with black holes. The only difference right now, and we're going to dig into that difference because that's going to be the point of this lecture, and that's going to answer the question how black is a black hole after Hawking, now that we know about all these radiations of Planck spectrum from the black hole. The question is this: kT times the Schwarzschild radius is equal to 1/2 hc over 2 pi, h bar c over 2 pi. But with here, we've got a greater than or equal sign. So here we've got a lower bound and everything has to be higher. Here, however, these things are equal. So now we're looking at the inequalities, and how do we take this and get to the sorts of inequalities which brings these types of relationships closer to quantum, to the ones that we see in quantum mechanics. And we'll talk then about why that's important. Okay, let's go back to the early days of quantum and people like de Broglie, and let's talk about particles in a box. Once it was known that particles have wavelengths, just like photons have wavelengths, one of the subjects that people began to look at was the so-called particle in a box. And let's sort of draw this thing out. Okay? Take a box. Put some wavelengths in it, or let's just take a string. I'm not talking about string in string theory. I'm just talking about a piece of string like what you're vibrating. Any violin, any cello, any string instrument operates according to this principle. The strings are attached at one end and the other end, and the vibrations which can occur are then going to be determined and constrained by how far apart these are attached at the end. So if I've got a particle in a box, you know, I can do this. I can have sort of a half beat, or I can have a full beat, or I can have 1.5 beats, and so on. But particles are constrained by the box. And the diameter of the box, if we make this box a circle, and I say diameter deliberately, and I tie that back to why we're using the Schwarzschild diameter rather than the Schwarzschild radius, the diameter of the box is going to determine the wavelengths of the particles that can be trapped in that box. And conversely, the particles which cannot be trapped in that box because their wavelengths are too long. So now let's get rid of this particular box, and instead let's do a different box. Let's make the black hole a box. So here's our black hole, Schwarzschild black hole. And let's take the origin point here, and let's draw a line across here, and here is the Schwarzschild radius, and here is the Schwarzschild radius, and this whole thing is the Schwarzschild diameter. Okay? Now, let's talk about a photon, single photon. And photons are both waves and particles, as is everything. That is, regular masses are both waves and particles too. This is de Broglie. But let's focus on photons, okay? Let's consider a single photon, and let's visualize the photon by drawing it out like this, okay? There you go. 1 beat, okay? If you're using coordinates, 0, 2 pi, think of any sine wave. Y equals sine x, it reverts from 0 to 2 pi. So here is a single photon. We could talk about half beats, but let's focus on full beat photons. We're going to talk about putting a photon in the box. Now, Susskind did a very good lecture about 10 years ago. It's online. I'll put the site up when I post this to YouTube. But he went from the Bekenstein relation for the entropy of a black hole and showed, very nicely how what you do is you take photons and you drop them into a black hole and you watch what happens to the black hole as you do that. And he showed how one uses that as a vehicle for obtaining the Hawking radiation, which we have here from the Bekenstein relation from 1972 regarding black holes, the one in which the entropy of a black hole is proportional to its surface area. And one of the things Susskind points out in that lecture is that, if you have long wavelength photons, they're not going to stay in the black hole. The black hole can't absorb them because they're too long. They're particles that can't be trapped in the box. On the other hand, if you have very short wavelength photons, those can be trapped in the box. We can have a photon, and I'll draw it right here. I'll make a little room here for our photon. So now, let's take this out. Let's take this out. And let's do the following. Let's just put the diameter up here. Here's the diameter of the black hole. And we're going to take a single photon. And we're going to put it in the black hole. A little more of a downward bump here. No, okay. There we go. What the heck? Okay. We're going to put a single photon, and this is going to be the wavelength of the photon using the gamma, which is, of course, commonly used to represent photons. So, what do we have here? We have a circumstance. Once again, my clock. We have a circumstance where if we're working with full beats, if we're going from 0 to 2 pi, we have a circumstance where any photon that has a wavelength longer than the Schwarzschild diameter will, as Susskind says it, will bounce off the black hole. The way I'd like to say it is those photons can't be trapped by the black hole. Those photons will have to be emitted by the black hole if they ever manage to get into the black hole. And those photons, again, are those with wavelengths that are longer than the Schwarzschild diameter. On the other hand, if you have a photon with a wavelength shorter than the Schwarzschild diameter, then that photon can get stuck in the black hole and it can't get out. It becomes a particle trapped in the box. So the answer to the question after Hawking, how black is a black hole, would seem to be that a black hole is not black as regards photons with wavelengths which exceed the Schwarzschild diameter, correct? But it is black. It does not allow to escape at all. those photon particles which get trapped in the black hole box because their wavelengths are shorter than or equal to the Schwarzschild diameter. We'll, just for purposes of this discussion, say that if a photon has a wavelength exactly equal to the Schwarzschild diameter, maybe it gets out, but you know, that such an infinitesimal slice, it probably doesn't matter. So this is what we're looking at physically. This becomes our boundary. A photon with a wavelength equal to the Schwarzschild diameter is the boundary between what gets out and what stays in, and what cannot get out. The particles which are not black, which get out, versus those for which the black hole is black, in the sense that nothing gets out. For these particles with shorter wavelength, the black hole is just as black as it was before we found out this from Hawking. You know, for the time from 1916 to 1976, I believe it was, so 60 years. For that 60-year period when we thought black holes were black, for these photons, black holes are still black. So let's take a look. Let's do a few calculations. Okay, the wavelengths of the photons which will be emitted, and that is what we have here, are going to be those which are greater than the Schwarzschild diameter, or perhaps greater than or equal. We're not going to worry about this right now. And the cutoff at which photons become trapped in the box is equal to the Schwarzschild diameter. So if we go back to these equations here, wherever we have a Schwarzschild diameter, we can now substitute the cutoff wavelength. So what we can find out from, which one is it? From this equation here, which gave us the 1/8, we've now changed the Schwarzschild diameter to the cutoff wavelength. And what we find using the exact same numbers is that the wavelengths which are emitted over the lambda peak are those wavelengths which are greater than about 1/8 of the Wien peak. In other words, for a black hole, all the photons, if 1/8 is here, all the photons over this part of the spectrum are going to get out, and the black hole is not black. All of the photons in this little piece below 1/8 are not going to get out. They're going to be trapped. Now, we can see, apparently, you know, from the shape of the Planck curve, and knowing that it is an exponential, when you get it, it's e to the minus x, so it's a negative exponential when you get to this area. When you get to 1/8, there are very few photons which fit the bill of being that short in wavelengths. These are very ultraviolet photons with respect to everything else in the spectrum. But it's the photons in this zone, right here. Those are the photons that can't get out because they get trapped in the box. Now, once we get there, we can take the same thing and let's go to the temperature reciprocity relation. Here we're going to this thing over here, but the Schwarzschild diameter is now replaced by the wavelength of the photon because of this, and the photons which get emitted, that's again lambda here, is the photons which get emitted. I'm not putting any emitted subscript on them. You could do that if you wanted to. Let's keep it clean. Are going to be greater than or equal 1/2 h bar c over 2 pi. And now we have gotten ourselves the inequality that we see in the uncertainty principle. We come back to this again, do the comparison, and I should have had a kappa over here, or excuse me, not a kappa, a Boltzmann constant. There we go. So Boltzmann's constant times T now gives you an energy, and this is an energy, and it gives you a wavelength, and this is a spatial limitation. And lo and behold, the wavelengths that are emitted, or the relationship which describes the wavelengths which can get out of a black hole in relation to the temperature of the black hole, has exactly the same form as the uncertainty principle measurement limitation, and the only difference being a factor of 2 pi. So you can just take this and do something like that to reduce something in those equations, and you have something that looks almost identical in form. So that's the crux of what I wanted to communicate this evening. The question then is this. And by the way, let me mention one other thing, and then I'll sort of conclude with some of the big picture takeaways that I'd like you to consider. Okay, let's also talk about the Bekenstein bound and the second law of thermodynamics. I'm just going to mention them right now. This is a preview for the next talk or two as we develop further what we have here. If you take the Bekenstein bound and you just algebraically restructure it, you can write it to say, and I mentioned this last time, that the energy of the Bekenstein system times its effective radius is greater than or equal to 1/2 h bar c times the entropy. I should have made that S a little bigger, but okay, that's the entropy over pi times Boltzmann's constant. Once again, you have an inequality with an energy times a length greater than or equal to our friend 1/2 h bar c, this time entropically amplified, or entropically tuned by this dimensionless ratio. We also have inequalities which come out of the second law of thermodynamics, written as entropy, change in entropy, is always greater than or equal to 0. And of course, it's well known that one of the physics pieces that goes into deriving the Bekenstein bound from the Bekenstein black hole entropy is the second law of thermodynamics. That's how you get the inequality here when you're starting with the equality that applies to a black hole in the original Bekenstein relationship. So now let's get to a couple of other questions that are related to this. I mentioned that and showed how the photons for which a black hole is still black in the pre-Hawking sense are those with wavelengths only in this tiny area. The curve here has already come way, way, way down because of the exponential that is in that curve, the 1 over exponential, or the e to the minus x, which is in this section. Again, this is the original Wien law before Planck developed his formula for the Planck curve. The Wien law described this section, Rayleigh-Jeans described this section. Planck put those two together, but he found that to do it, that the energy had to be NH times the frequency, and I wrote that very poorly. Let's write that a little better. Okay, so we've got Rayleigh-Jeans and Wien, but the point being that this is very small. Now you can calculate this, and when you do the calculation, the question is, how black is a black hole? Well, you can calculate that the number of photons that are in this domain, below 1/8 of the Wien peak, or below 1 over 7.95 and some extra digits of the Wien peak, that How much of the black hole is black? Black question mark? One photon, and I should probably make clear that this is a 1. One photon per 2.049 times 10 to the 14th. So the number of photons, which, sorry, being a little bit of a klutz today. The photons not very many photons. A black hole is black in the traditional sense, in the pre-Hawking sense, for 1 photon out of almost 1 quadrillion photons. 1 out of 0.2 quadrillion. 1 out of 200 trillion photons, or 204 trillion photons. That's a very tiny number of photons, but the black hole is going to hold those back. And that is the answer to the question that we posed as the title of this talk. Now, let's go back to what we talked about last week, the geometrodynamic vacuum. That vacuum, which permeates everything, which has a temperature on the order of 10 to the 30th Kelvin, and where you have Planck length fluctuations on average, separated by the Planck length on average, did I say Planck mass fluctuations, separated by the Planck length, gravitational energies, which are equivalent to the Planck masses. Everything is a black hole. Everything has a spectrum. And that means that that vacuum is also going to have a cutoff at 1/8 of the peak. And it turns out that 1/8 of the peak is equal to 4 times the Planck length, so that the peak itself is equal to about 32, slightly under 32 times the Planck length. But that vacuum is also going to be cutting things off. Now, let's do a little bit more drawing here. I'm going to turn the blackboard over. And we're going to see how all this works with 2 sides. Okay. Now, let's go into the vacuum. So we're in the Planck vacuum. And you have all sorts of black holes. So let's take some fluctuation, call this here, and let's say that the Planck length, let's take a fluctuation at the Planck length, and then let's take a larger fluctuation, which is greater than or equal to the Planck length. So, you know, and then you've got some very small fluctuations, and you might have some really huge fluctuations. I didn't make this much bigger than that one, but you get the point. So now, one of the questions you think about, if you're thinking about this statistically, using statistical thermodynamics, or keep statistical thermodynamics in the back of your mind for a moment. Let's say that this is a fluctuation, which is a Planck mass fluctuation, and its size is the Planck length. So this is larger black hole, this is even larger black holes, these are smaller, these are smaller. But these things are all packed against each other inside the vacuum, and they're very, very, very dense. Again, you're talking about 10 to the 90th kilograms per cubic meter. That's an enormous density. So one of the questions is this. Let us start with this tiny black hole. Well, the photons which are trapped are going to have extremely short wavelengths, but a photon can easily get out of this black hole, you know, if it's got a wavelength like this. But these are all packed up against each other. So this photon, while it can't be trapped by this tiny guy here, by this fluctuation, might be trapped here, and it might, if it encounters a Planck mass, it might be trapped here. And there are going to be some larger fluctuations in that vacuum statistically also. So even longer wavelength photons that might not get trapped by the Planck mass can be trapped by some of these larger ones. Again, I didn't make that too much larger. But the point being that in the end, because of the fact that a photon, which might be emitted by a very tiny black hole with a small mass on the small end of the statistical spectrum and a small size on the end of the statistical spectrum, and again, because the Schwarzschild radius is proportional to the mass, Rs equals 2gm over c squared, radius and diameter proportional to the mass, those black holes are going to, or those photons are going to get trapped by some of these others. So you get a cutoff from the vacuum. Despite the statistics, the cutoff is still going to be at about 1/8 of the peak of the vacuum, and that's approximately equal to 4 times the Planck length. So the vacuum cuts off also is going to be black for some number of photons that are emitted in the radiation spectrum. That's important because the vacuum is holding back those black holes. Now we're going to get back to the other screen. And I think the final point for this evening is this. We have a vacuum, the geometrodynamic vacuum, the quantum geometrodynamic vacuum, which Wheeler laid out in the 1950s. Due to what we learned from Hawking and Bekenstein in the 1980s, we know that vacuum is going to have black holes. They are going to have a black body spectrum. Based on what I showed here, that vacuum is going to cut off any emissions of photons below about 1/8 of the peak Wien wavelength for the vacuum. So now here is the question. Could it be, and I pose this as a question, that when we observe an ordinary black body, when we take something that is going to absorb all light, and we put a little hole in it, and we heat it up, and that heat, the only things that are going to emit this spectrum, it's not the body itself, it's the cavity inside. And that cavity ideally is a vacuum. And that vacuum is emitting a radiation spectrum. And you go into outer space and you look at the CMRB, and that is a vacuum, go out to the end of the solar system, go into intergalactic space. There's not much floating around there, but you still got the CMRB at about 2.7, if I recall correctly, degrees Kelvin, having a black body spectrum. So it's out there. The question is whether, when we are doing experiments to observe a black body, what we really are doing without knowing we are doing it is observing the quantum geometrodynamic vacuum, first articulated by Wheeler, now having to be understood in terms of Hawking and Bekenstein, to have a radiation spectrum, and whether we are in fact simply observing that vacuum with a reciprocity relationship that looks like this, or that looks like this. Now, I'm going to conclude this talk by doing what they do sometimes at the start of a movie or at the start of a series. They show the end first, and then everything else is development to see how you get to the end. I'm going to make a statement. This is from me. This is my personal assessment of the physics that is going on here, which is simply this. I say that when we observe an ordinary blackbody spectrum, when we heat up that cavity to a certain temperature, and we observe this coming from the cavity, the same thing that Planck characterized in 1901, the same things that before the turn of that century, Raleigh, Jeans, and Wine, and Boltzmann, and lots of other people at that time were trying to get their hands around. When we observe a black body, we are in fact observing that vacuum that Wheeler first exposited in the 1950s with the updated understanding of Bekenstein-Hawking from the 1980s, using a reciprocity relationship that looks like this, which is similar to the reciprocity relationship that obtains from the uncertainty principle, but it is a temperature wavelength reciprocity rather than an energy applied spatial resolution Heisenberg microscope limitation, which describes what happens in particle physics. That is the hypothesis. That is what I am proposing is in fact the actual physics of when we observe a black body. Now, quantum gravitation. These are theories that are very difficult to prove. Why are they difficult to prove? Because you're talking about things in the Planck scale vacuum. The energies for this guy required to probe to Planck length resolutions are 10 to the 15 smaller or more energetic than the best we can get with our best accelerators. So we have all sorts of theories about quantum gravitation, but we have not found any good experimental way to confirm these theories. And the prevailing view is that, geez, I don't know how we're going to find an experiment that's going to confirm something. Well, I'm making the hypothesis that that vacuum is the source of the blackbody radiation that we observe. When we observe blackbody radiation, we are observing the quantum geometrodynamic. When Planck put these two things together and it produced quantum mechanics, or it started the quantum revolution, what people did not know, and what people still do not know today, 121 years later, is that this curve is describing the emissions from the quantum gravitational vacuum, from the physics at which gravitational theory, general relativity, and quantum mechanics are unified. But how do we test this? How do we find out if this is true? What we need to do is an experiment, and I will be going through in the next few talks the reasons why the experiment leads to this. If what I am saying is true, then even in the blackbody emissions that we observe from an ordinary blackbody, you're going to lose the photons in this section here. You're going to lose one photon out of every 204 trillion photons. Nobody will casually come across that just doing experiments to look at that curve and to say, yeah, that curve looks the same as it's always looked, because we're talking about this area over here. You have to count photons, you have to do it carefully, and it can be done with equipment that we have today. Again, I'll talk about that in a future talk. And I am predicting, I do predict, that when you do that, with an ordinary black body, you will in fact find that when you get below the Wien peak, because of the fact that that black body radiation is emerging from the geometrodynamic quantum gravitational vacuum, you will lose these photons. This is the part where a black hole still is black. The blackness, the remaining blackness of a black hole accounts for this. And if you can confirm this cutoff, or this cutoff at 1/8 of the peak, that leads to this very small loss of photons by looking at what's coming out of a black body and doing a suitable photon counting experiment near this, you will find that this happens. And that will give you confirmation that ordinary black bodies are simply the quantum gravitational vacuum being viewed with a reciprocity relationship from a temperature far removed from the scale of that vacuum. That is where we are headed with the talks. Let me see if there's anything else that needs to be added. Yes, one other thing. This cutoff at 1/8 of the peak, I have obtained here tonight through this, by regarding the black holes as a particle in a box. But now the question arises, is there an independent theoretical confirmation that we can have for the cutoff being here, being at this position? Is there a theoretical way to confirm it? Beyond the experiment that I'm also talking about, which I believe is going to confirm it. And the answer is yes. Because if you start with the Bekenstein bound, and you also use the second law of thermodynamics, and you also, I will simply mention one other thing, and you use the fact that for a closed system, the total energy of that system, change in energy, or the differential of the energy is zero. Energy is conserved. If you take these three pieces and combine them together with what we know here, just here, none of the black hole stuff, just the Wien law. Combine this with this and this and this. Turns out that the greater than or equal sign that is in the Bekenstein bound turns into the exact same greater than or equal sign you see here, so that the consequence of the Bekenstein bound, the second law, conservation of energy, and Wien displacement law means that, in fact, from those four pieces of known physics, there is going to be a cutoff in a black body spectrum emission. That cutoff will be also predicted at the exact same spot, 1/8 of the peak, this number of photons that are still held by the remaining blackness to 1 part in 204 trillion of a black hole. That's where we're going with this. I will talk about the experiment. That may be a couple of talks downstream, but we will go there. I am going to offer that prediction. And for anybody who wants to bet a farm, I will take that bet. Thank you and good evening. It's been a pleasure. Until next time. I will say we've got a number of family events coming up the next several weeks personally, so it may be several weeks before I return for the next talk. But I think this should be good for now. And again, I thank you for listening. Good evening, good day, wherever you may be on this world, and peace be with you in these rather trying times that we're still living through in the opening years of the 2020s. See you soon.